So in this video I'm going to have a look at the binomial theorem. And the binomial theorem is if you have a sum, and traditionally it's written a plus b, we have two terms, hence by, and you raise it to to a power of an integer. In this video I'm going to use example a plus b to the power of 4, and we want to expand this. And there's actually a formula for this. If you study IB math and you look at your formula booklet, you have this formula, which is true, but maybe at first glance doesn't seem so easy to use. So what we are going to do is we're going to look at how you get to a formula, and we're going to use a question of combinations. So let's start by actually looking at what this means. Well, if you have a plus b to the power of 4, it means a plus b multiplied by a plus b multiplied by a plus b multiplied by a plus b. And with this we could solve using ordinary algebraic tools, and what I'm going to do is I'm going to use these techniques, and then as we do that, we'll see both that method is too cumbersome to be of real use, and how we can use that to build up to a more easy formula. But if you wanted to do this, you might start with taking these two brackets, leaving those out of it, taking only these two. So we know that a needs to be multiplied by a and with b, and b should be multiplied by a and b. So what we'll get is a times a is a square, plus a times b is a b, and b times a is a b, and b times b is b square. And then we have, of course, this needs to be multiplied by the other two brackets, a plus b, a plus b. And you might say, well, these two terms are the same, they should be merged. And yes, you're right, but I have a reason for wanting to keep it this way, because I want to plant a thought that we'll come back to. We're going to end up combining the different terms in each bracket, and we're going to end up with each possible combination, so each a and each b from these brackets together. So now if you want to continue, you could look at this and say, okay, so we need to do this a squared by a, and this a squared by b, and this ab by a and ab by b, and this ab times a and ab times b, and b squared times a and b squared times b. As I said, this, if you think this is tedious and cumbersome, yes, you're right. This is not how you would be expected to solve the question, but it is the reason why we have the formula we have. And so before we go on, I just want to write down what we said before, that in the end we're going to end up with every combination of a and b from each bracket. So let's rewrite this, and we're going to see a pattern emerging. So a squared times a, that's a cubed. A squared times b is a to b. AB times a, so it's a to b plus AB times b, AB2. Then we have the same, a to b plus AB2. And finally we have b squared times a, that's AB squared, plus b squared times b, that's b cubed. And then we would have to take all of this times a plus b, of course. The last bracket we haven't touched yet, we haven't expanded that. And now it's even more obvious that we should really merge the terms here. So we have just one a cubed term. But we have this a squared b, and this a squared b, and this one. So there are three of them. We also have ab square, and ab square. And then we have a b cubed, sorry. And all of this times a plus b. So there's a pattern here that we're starting to see. We have the higher powers towards the end, looking just at this bracket, which is the same as a plus b raised to the power of 3, like the whole bracket raised to 3. And then we have higher coefficients in here. And in order to actually see the pattern we're looking for, we're going to do the last manual step of multiplying every term in here with a and every term in here with b. So we'll get a cubed times a, that's a to the power of 4, a cubed times b, a3b, plus 3a cubed b, plus 3a squared b squared, plus 3 a squared b, square b square, plus 3ab cubed plus ab cubed plus b4. Yeah. So obviously again it's necessary to merge them if we want to have any control of them. And we see we have just one a to the power of 4. I'll actually write that out as 1 a4. And then we have a cubed b plus 3a cubed b, so that's 4 of them. We have 3a squared b squared and 3 more a squared b squared, that's 6 of them. 3ab cubed plus 1ab cubed. And finally, one last b4. And in order to see the pattern here, here we have all a's and b's in each term. Here only a, well, we could actually though write that as b to the power of 0, because that's 1, so it doesn't matter. And here, seeing that it's a lonely b, I'm going to put in the exponent of 1 there. Same in this end, A1 and plus 1, A0, B4. And now we see the pattern that each term will have A to some power times B to some power. And those two powers, the exponents of A and B, always add up to 4. This is not really so strange. We come back to the thought of combinations up here. For each of these brackets, each of these terms represent taking either A or B from each bracket and multiplying by each other. So the question really comes to, how did we get this 4? Could we have known that it should have been 4? Well, this term is A times A times A times B. And it comes from combining A or B from these 4 brackets. Basically picking an A or an B, because all combinations are included in here. It's just that some combinations turned up more than once and therefore have been merged. So how many combinations could I take which would give me 3 A's and a B? Well, I could have taken that A, that A, that A, and that B. Or that A, and this one, and that B, and that A. Or A, B, A. Or I could have taken this B, and then the A, and the A. I mean, there's only one way of getting 4 A's out of it, and that's taking this, and that, each A. But when I get to take 1 B and 3 A's, I have more of a choice. What about the 6 then? 2 A's and 2 B's, and that can be done in more ways, and it's a bit tricky to keep track of all of them, but basically you could say A, B, B, or A, B, or A, B, A. Or you could start with a B and say B, A, B, A, B, A, B, 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 A. Let's write them down, it'll be clearer. So we have a string of 4 letters, A or B, and we need them to be 2 A's and 2 B's, and that can be A, B, B, A, B, A, B, A, B, B, A, or it could be B, A, B, B, A, B, A, or B, B, A. That's 6 of them. Those are the only combinations with 2 A's and 2 B's. So really, I could look into this if I wrote down all possible combinations. And I have actually done that. So, let's look. So these are the 4 possible combinations, the 16 combinations of 4 letters, either A or B. And if we look at the coefficients, we'll see that they match. So there's only one of these 16 that gives you 4 A's. It's this one. But there are 4 of them that will give you 3 A's and a B. It's this one, this one, this one, and this one. There are 6 of them giving you 2 each. So it's 1, 2. I mismarked one, didn't I? Yes. This should have had red cross, sorry. Because this is blue. So that's 1, 2, 3, 4, 5, and 6 of them with 2 A's and 2 B's. And then looking at those with 1 A and 3 B, we find 1 there, 1 there, 1 there, and 1 there. So there's 4 A1, B3. And then there's 1 single B4. There's only one way of combining them to get all 4 B's. So really, if you have, when we have A plus B bracket raised to the power of 4, we now see that we're going to get 5 different terms. We're going to have an A4 term, we're going to have an A3B term, an A square B square term, an AB cube term, and a B4 term. And then the coefficients here, it's going to be 1, 4, 6, 4, and 1. And really, this pattern will always happen, and it really comes down to how can you figure out these coefficients. As we saw, if we look at this coefficient, it's a question of this. Out of 4 possible A's, in how many ways can you choose 2 of them? And this we would like a way of figuring out, preferably without resorting to writing down each combination and color coding and counting, because that's tedious. And luckily, there's a way. This is a well-defined mathematical question. If you have a group of elements, of things, you want to choose a subset of them, in how many different ways can that be done? And we call that, we actually write this 4C2. 4, choose 2. Out of 4 elements, choose 2 of them. Or sometimes we write it like this, 4 and 2 and brackets. This is not a fraction. There's no division here. It does look like it, but it's, well, I mean, there's a dividing dash missing. So don't mix this up. Don't confuse it with a fraction. And in this case, we also have a formula, which I will present without proving. And it's 4 times 3 times 2 times 1 for neatness, divided 2 times 1 times 2 times 1, which turns into 24 divided by 4, so that's 6. And more generally, we have that if we have n elements and we want to choose r out of them, which is the same as we sometimes write then n choose r. This is n factorial, the product of all integers from 1 up to n, so 1 times 2 times 3 times up to n, divided by r factorial and n minus r, everything factorial. And the reason here we got 2 times 1 and 2 times 1 is, of course, that 4 minus, here it's r factorial, so it's 2. And here it's n minus r, that is 4 minus 2, but that's 2 as well. So this formula will give you each and every of the coefficients there, which is handy. So if we sum this up, we have that a plus b, everything raised to an integer n, will be a sum, will be expanded into terms where we have in each term we have a and b in such a combination that their exponents add up to n. So if n was 8, we would have a5 times b3 and a to the power of 1 times b to the power of 7 and a to the power of 4 times b to the power of 4, every different combination of a and b with a combined power of, in that case, 8. And the coefficients for these will be n choose 0 times a n b 0 plus n choose 1 times a n minus 1 b 1 plus n choose 2 times a to the power of n minus 2 times b squared plus and so on, all the way up to n choose n times a to the power of 0, this is 1 but we write it for neatness, times b to the power of n. And all of these coefficients are given by the formula. If you have n and want to choose r elements out of it, it can be done by computing n factorial divided by r factorial times n minus r factorial. This can also obviously be calculated by your calculator if you have it. And if we look at the formula we had from the beginning, it's the same, which obviously is not a coincidence. I mean, this is the formula for the binomial theorem. And what we've done now is to go through and seeing why is it that the combinatorics, the question of choosing and combining the terms a and b and how many ways it can be done, turns up as the coefficient of this expanded sum. If you look around, you'll find lots of videos about this, and some of them, or a fair amount, will also combine it with this, which you might have seen already. It's Pascal's triangle. And it's another way of arriving at the values of these formulas by doing this pattern where you have rows with ones on either side, and then each number is a sum of the two numbers above it. So here we see, for instance, this is row 4, supposing that you start counting by 0. So 0, 1, 2, 3, and 4. And you have actually the coefficients 1, 4, 6, 4, 1. This is very, very handy, but possibly more of a neat way, while this formula is also including the reason behind it. And as with everything, practice is the way of getting control of it. So, good luck.